of this problem um, wants us to plot a graph. So given this equation for force in terms of time, we want to plot a graph of force versus time. And so and we're plotting it from 0 seconds, to 0.003 seconds. So the simplest thing to do here will be to plug in f at t equals 0 and f at t equals, or plug in t equals 0 for f and then t equals 0.003 for f, and get get those two extreme ends. And then you notice that this is a linear relation, so we don't have any curves going on here. So there's a constant there's a constant slope from the 0 point to this end point, and you plot that there. So you don't really need to plug in values every every few steps or whatever. You can just plot the endpoints and use a linear relation. Anyway, you plotted that. In part B, we want to use graphical methods to estimate impulse. So impulse, as you'll remember, is just f times delta t. And so you want, in this portion, the area under the graph, right? And then area under the graph would be approximated as area of a trapezium. And so think of, and so the trapezium is this four-sided figure, and whose area is given by 1/2 times the base, or height, or whatever, let's call it height, times a plus b. So this the sum of these of this side and that side, and so the trapezium we're interested in here, right? That's the trapezium we're interested in here will just be so J equals area will be 1/2 times height, which is basically just the time at the end, so 0.003 seconds, times a plus b, and so that would be 740. Here to here it's 740, and then here to here it's 50. So times 740 plus 50 newtons. Okay, and so the area will be 1.2 Newton seconds. All right, that's by the graphical method. In part C, we use integration, and so here we integrate f over d with respect to dt over the interval t equals 0 seconds to t equals 0.003 seconds, right? So we integrate 740 minus 2.3 times 10 to the 5 times t with respect to dt from 0, t equals 0 to t equals 0.003. And so this the result of this integration is 740t minus 2.3 times 10 to the 5 divided by 2, so 1.15 times 10 to the 5 times t to the 1 plus 1, so t squared. And that is evaluated from t equals 0 to t equals 0.003. And what you get from that is 1.185, which is approximately 1.2 Newton seconds. And this tells us that this was a more accurate method, but nonetheless, the answers are approximately the same in B and C. Okay, in part D, we want to find the mass of this bullet. So the impulse is equal to mass times change in velocity. So mass is just impulse over change in velocity. And so that's impulse of 1.2 Newton seconds over change in velocity is 260 meters per second. And so we get 4.6 times 10 to the negative 3 kilograms, which is also 4.6 grams for the bullet's mass. And finally, in part E, we invoke momentum conservation. So P initial is equal to P final. Initially, you have no velocity for the bullet or the gun, so 0 momentum. That is what the final momentum has to be. So that is mass of the bullet times mass of the velocity minus mass of the gun times velocity of the gun. And so that means that velocity of the gun is the momentum of the bullet over the mass of the gun. So that's 0.0046 times 260, which will be 1.2 over 4.5, giving us 0.26 meters per second for the velocity of the gun. And that's it.